Let's continue our study of stochastic analysis. And last time we discussed the notion of stochastic derivative for random variables which are measured with respect to standard Gaussian random variable. The notion was based on the very nice property of Hermite polynomials, namely, I recall that we defined Hermite polynomials for the polynomial of order k from x with the help of formula hk of x is equal e x over 2 multiply minus 1 over k. Here is d dx in k power applied to x minus x square over 2. And one of the important properties of hk was the following. It occurs that if we take the derivative of Hermite polynomial, it will be equal to the Hermite polynomial of degree k minus 1 multiplied by k. So the differentiation of Hermite polynomials is similar to the differentiation of powers of the variable x. Based on this property and on the property of orthogonality of Hermite polynomials with respect to standard Gaussian distribution, we were able to proceed as follows. If we have a random variable alpha, which is square integrable and measured with respect to standard Gaussian variable, then alpha can be uniquely expanded as orthogonal series from Hermite polynomials of psi. This is equal to 0 to infinity, ak, hk, psi. And finally, one can try to define the stochastic derivative of the random variable alpha d alpha as a sum k equals 0 to infinity, k hk minus 1. This is not prime. This is a gap on my board. Hk minus 1. Of course, if this series converges in square meter. Last time we discussed that there are a lot of random variables which have stochastic derivative. For example, if we know that our random variable has the following property, it is a square integrate and measured with respect to sigma field generated by psi, then alpha can be represented as f of psi. We know this with some Borel function f. And it occurs, last time we checked this, that if f is bounded and has a continuous bounded derivative, then so if f belongs C1 and f prime bounded, bounded. Then d alpha exists and it's equal exactly f prime. So one can imagine that the notion of stochastic derivative is closely related to the notion of the usual derivative, which we know from the course of calculus. It is true, and first part of our lecture today will be devoted to understanding deeply this connection. Namely, we will answer the following question. Firstly, since it looks like usual derivative, it is natural to ask, maybe it is the same. There are no other stochastic variables which are stochastically differentiated. The answer is negative. We will see that the set of such functions for which this random variable has stochastic derivative is wider than this set of differential functions in the usual sense. So this is the first question. Second question is the following. As we remember, even not from university, but from school years, the derivative is the limit of some ratio. We shift something and take a difference and divide on the length of the shift. So this procedure also was very helpful because based on this definition of derivative, we were able to say the Fermat theorem about the necessary condition of the maxima of function, or for example, one can check Lagrange theorem, Cauchy theorem. And so there are a lot of important properties of differential functions which are based on the definition of derivative as a limit of some ratio. So we have to ask what happened there, because our definition is completely different. We use the following, one can say, algebraic approach in order to define stochastic derivative for random values. But we will see that in this case we can propose some more convenient for first meeting definition of stochastic derivative, which is more or less the same as in usual calculus. So let's start. And firstly, let me show you that the set of functions f for which this random variable has a stochastic derivative is wider than this. Yeah? In order to do this, I will apply some notions from functional analysis. I will give a characterization of stochastic derivative from the point of view of functional analysis. Namely, let us consider this space A2 sigma psi as a Hilbert space. Yeah? It's a Hilbert space. This is a separate Hilbert space. Hilbert space. By the way, don't believe me, easy. So let's answer the question, why it is separate? The hint here is the following. sigma psi is countably generated sigma field because it is generated by the sets like psi less than some rational number. So this is countably generated sigma field, and consequently, you have to prove this, it is separate from that space. Then I can consider the following construction here. Let me denote by W1. It will be the set of all random variables alpha. I will not say that they are from here. We discuss only this case, yeah? Alpha such that there exists D alpha. Yeah? It means that this series converge. Let me write it. Yeah. This series converges in square. Then I can consider the following construction. I have this Hilbert space L2 sigma psi. I have a subset W1, and I have operator D, which x equal to sigma x. So I have a very common construction from functional analysis. I have a Hilbert space and a linear operator in this space. Now let us look for the properties of this operator. So let's check some statements. The first is trivial. Namely, W1 is dense in L2 sigma. Why it happen? Because if I consider such set, P is a set of random waves of such kind, P of psi, where P is a polynomial. Is a polynomial. Then, of course, P is included in W. Why it is happening? It is trivial because every random variable from here has a finite expansion with respect to Hermite polynomial. Yeah. Due to this, it is trivially stochastically differentiable. So we have such inclusion. And from other side, we know that any random variable from this space can be represented as a series of Hermite polynomials. So partial sums of this series are exactly elements of. So it is trivial. Another property is not so trivial, but it's very useful. Namely, D is closed. On W1. So if we consider this linear operator with this domain of definition, it is closed operator. Let me recall you what means closed. Here. If we have a sequence, let me, for example, alpha n, random variables from the domain of definition, such that we know that d alpha n converges to some variable zeta, and we know that alpha n converges to some variable kappa in the square mean, of course, in the square mean. So in this space, and the n tends to infinity. Then this random variable kappa belongs to W1 and d of kappa equal to zeta. So the property to be closed is slightly weaker than a property to be continuous. Of course, a continuous linear operator, which is defined in all space, is closed operator. But our operator D is not continuous. And it is, again, a good exercise to check that D is not continuous operator. So we cannot, for free, just expand it on all space. This is, by the way, a hint how to check that D is not continuous. Is not continuous operator. Please give an example of such random variable which has no stochastic derivative. It is not too hard because you have just take such coefficients an that the corresponding series for stochastic derivative will not converge in square. So I claim that in our case we have not continuity, but we still have some good property of this stochastic derivative. It is closed operator. Let's prove this. Let's prove. The proof is not very good as exactly in the previous case. We will use the form. Define P with index of n of random variable alpha. Let it be the coefficient. Let it will be the an multiply hn psi, where when we take this an multiply hn psi from the orthogonal expansion of our random variable. So we consider the series which represent our random variable alpha. Alpha is equal to sum from k 0 to ak hk of psi, and then we just ask not all series, we take one summand with index n. Then it can be trivially checked that if alpha n converge into to our random variable kappa, then p k alpha n converge to pk kappa, and it happened for any k which is greater or equal than 0. Why it is so? Because this is orthogonal projection. Every Pn is orthogonal projection. So Pn is orthogonal projection. In the future, I will not say orthogonal because we are working in Hilbert space, and it is natural to take namely orthogonal projection. So I will say just projection onto the following subspace. Here is some H, Hn, psi, H belongs to. This is one-dimensional subspace of our L2. Then, due to this property, Pn, of course, is continuous operator. So if this convergence holds, then this convergence must hold. Moreover, by the condition of our statement, we have that d alpha converge to some element zeta alpha n when n tends to infinity. Then pk of d alpha n converge to pk of zeta when n tends for any k which is equal to 0. Okay, but what happened? We know how this pk of d alpha n looks like through this one. Namely, we know from the definition that now pk d alpha n is equal to k plus 1 pk alpha n. Yes, this is just from the definition of our stochastic derivative. And now let's see. This expression goes to this one, and this expression goes to this one. So I have a relationship between this and this. Namely, now I can say that the following relation holds. I have that pk for zeta is equal to k plus 1 k plus 1, or excuse me, k plus 1, k plus 1 of alpha, not alpha, but kappa. Okay. Finally, from these two relationship, or we have such an expression. And it follows from that that exactly d of kappa is equal to zeta. And kappa belongs to the 1. This is exactly our state. So now we know that the stochastic derivative is a closed linear vector. Now it is good to go back to our example from the previous lecture, and consider the following special random variable alpha, such that alpha is equal to f of psi, where f belongs to C1, R, and f and f prime are bound. Let me take now arbitrary beta which belongs to our set P. So this is polynomial from psi. Beta is equal to polynomial. Of course, it has stochastic derivative for free. Yeah? But now what I want to say that now there exists a sequence of such fn such that they satisfy this condition, and f and psi converge to beta, f and prime psi converge to d beta. It means it is two sense. Why it is so? What we have to do to get such a sequence? We just have to approximate polynomial in two sense with respect to standard Gaussian distribution by the continuous and continuously differential function which are bounded with boundary. So what we do, we just do some smoothing of the. We just cut polynomial on some level, then smooth it with the help of infinity differential function. You face such a construction a lot of times in course of equation and partial derivative equations and in course of analysis. So we just do such approximation, and then we have such kind of convergence. And finally, it means that I can do the same for arbitrary, which belong for beta, which belong W1. Why it is so? Because I can take the sequence of Pn of psi such that it will converge to beta, and dPn of psi will converge to d beta, Why it is so? Because as these polynomials, I can take partial sum of our expansion of beta. Due to the definition of stochastic derivative, we'll have such conversions, but we can approximate every such polynomial by these functions. Yeah. So finally, we can take such sequence for any beta which belongs to W1. From this point of view, one can now understand why I choose this notation W, because now the construction of stochastic derivative occurs to be exactly the same as the construction of the Sobolev space in mathematical physics. Why? We just take smooth functions and say that beta belongs to W1 if and only one can approximate beta by this smooth function in such a manner that this converges to some to some functions, by the way, in L2 sets. So one can now understand that W1 is Sobolev space with respect to standard normal distribution, standard Gaussian measure. In mathematical physics, we usually use here Lebesgue measure instead of a Gaussian measure, but the flavor is the same, exactly the same. So, in this way, we understand that with every beta, which belongs to W, we associate this representation f of psi, and d beta is equal to f prime psi, where f prime is Sobolev. Namely, again, limit in the square mean of the usual derivatives when we approximate function. So let us ask, which properties have this function f? Will it be with necessity differentiable or not? It occurs that not, that no, f don't have to be continuously differentiable in order to have stochastic derivative. Let us see some examples. Consider a random value beta, which is simply absolute value of x. Yeah. So now in this representation, our f of x is equal to absolute value of x when x is a real number. Of course, this function is not continuously differentiable because at the point 0 it has no. Let us check that it is still that this random variable still is stochastically differential. How one can check this? I think that we can proceed as follows. Let us consider a graph of this function. And now do the following approximation. Just like this. Yeah. I will do this smoothing in such a way that we will change every time our function on a very small interval. Yes, a very small interval. So how I can do this? I just can take parabolas with like and x squared, and then try to find here. Just take this parabola this way up to the moment of heating of our graph, and then we get such a smoothing of our function. Now let us see what happens. After I do such smoothing, I give such smoothing, what we will have? Look, this function here will have a derivative, but this derivative in the absolute value will be non-greater than 1. Yes, because we have here and here we have such a situation, just and then this is derivative in absolute value equal to 1. Due to this, one can understand that when I will have a sequence of such functions, say fn, then of course fn of psi will converge in these two senses. F of psi, and fn prime psi will converge in a two sense to something. But if it converges, then this must be stochastically differential. So we have this dx. And of course, this df can be identified. Df can be identified with the following. Df of psi is just sine of psi. Yeah. It does not matter how we define sine in the point 0 because it has psi hit 0 with 0 probability. So we have the examples which says us that now our definition of stochastically differential random variables includes such random variables which can be presented not only by differentiable functions of space. But we cannot go very far from good functions using stochastic derivative. Why it is so? Maybe people who studied mathematical physics now know very well that Sobolev spaces has a good structure, and we have well-known Sobolev embedding theorem, which says that for a special relationship between the order of the space and dimension of the initial Euclid space, where we define Sobolev functions, they became to be continuous. In our case, it is essentially easy because this is one-dimensional case, and I can say the positive statement holds of the following positive statement of the following type holds. This is a lemma that if alpha belongs W1 now, then there exists f which is continuous on the R such that alpha is f of x. Of course, f must be from the Sobolev space, but at least it is continuous. So, what we have to prove? Actually, we have to prove that any Sobolev function in one-dimensional case is continuous function. Okay? Let's check this. What I have the sequence Fn, which belongs to C1 such that f prime bounded such that the following conversions hold. Firstly, the integral with respect to r f n x minus f of x in square p1 dx p1x and dx converge to 0, and the integral with respect to r fn prime of x minus some function, say j of x p1 of x dx converge to 0 when n tends to 0. So now we have such two functions, and this is exactly Sobolev derivative of f. We want to show from this relationship that f can be chosen continuous. Why I say can be chosen? It is trivial because this is convergence only in square mean. So it holds for any function which coincides with f on the set of outside of the set of zero limit match. So I say can be chosen. This means that I can find such continuous function which coincide with this one outside of the set of Lebesgue magic 0. Let's do this. And note that from the relation 1 is 2. From the relation 1, we have that f and x converge to f of x when n tends to infinity for almost so I can find a dense set of x for which we have such convergence. Yes. So there exists a dense set M in R such that for all x which belong M, we have this. Then let us consider difference. Let us consider a difference. Fn of x2 minus fn x1. It converges to f of x2 minus f of x1 for n tends to infinity, and x2, x1 from m. Now it's time to use the second condition. Unfortunately, I have to write it, but you have it. Fn is continuously differential. So we have the following. This difference, let me do this as follows, is equal to integral from x1, x2 of f n prime x dx. Yes. Now I will suppose firstly that I consider our x1, x2 belonging to M intersect with some interval minus AA, where A is positive. Then I can continue and write the following. It's equal to integral x1, x2, here fn prime of x divided by p1 of x multiplied by p1 of x d. And due to the properties of p1 is separated from 0 on this interval, I can take absolute value. I can take absolute value of this and say that it is less than some constant. It depends on this interval a, but only on this interval. And here is integral from x1 to x2. Here is absolute value of fn prime x p1 x dx. And this, of course, goes to the integral from x1 to x2. Here is absolute value of this jx p1 x dx. Now I will say that this is equal to, unfortunately, I have to erase this one. This is equal to the integral with respect to r, absolute value of jx multiplied with the indicator of x1, x2 of x p1 x dx. By the way, here is CA, and here is also CA. Now let us apply Cauchy inequality. Less or equal than is less or equal than less or equal than CH norm of J in L2 multiplied with here is integral from x1 x2 square root p1 x dx. Again, the this is less or equal than some constant, new one, less than CA prime, and here is norm of J, and finally x2 minus x1 in 1/2. It means that on the set M, our function f is Hölzer continuous. And it means that it can be extended to the Hölzer continuous function on the all R. And please check that the convergence will hold for L2 in L2 mean exactly to this function. That's all. We have the continuity even more. We have continuity with such power. By the way, it means that one can very easily find continuous but not Sobolev functions. Yeah, just take the function which does not satisfy a Hölzer condition with 1/2. Yeah, and you will get the continuous function, but not from the Sobolev space. So now we understand a relationship between stochastic derivative and the set and the representation of the our random variable by the continuously differential function. The class of stochastically differential random variables is wide, but not too big relatively to the continuously differentiable functions. Now let's come to the second question. As you remember, we discussed the natural definition of the derivative. Yes. So if we have a good function f, then f prime psi must be equal to limit. And epsilon tends to 0. Here is 1 over f. Here is f of psi plus epsilon minus f of psi. And here is epsilon. So this is the usual definition. And it is interesting that we can adapt this definition to our case. Namely, again, I will suppose that f belongs to C1 on R, and f together with its derivative are bound. Then it can be checked that these functions, let me say it like, let me say d epsilon of f of psi, this random variables, which are f of psi plus epsilon minus f of psi divided by epsilon. Of course, now they are from W1, yes, they are now from W1, and moreover, we know that these functions one can check the conversion into f prime. So this is important, that one can approximate now the derivative by this expression. Converge in L2. Please check this using the Lagrange theorem and boundedness of this F prime. Then one can ask what happened in general case with alpha, which is stochastically differential. Then one can recall that if alpha belongs to W1, then there exists a sequence of such functions f such that f and psi converge to alpha and f and prime psi converge to d alpha under n tends to infinity. Where fn and fn prime where fn is continuously differentiable, such that fn and fn are bounded. Convergence is in two sense. Now, what happens if we proceed as follows? Let us define fn, this d epsilon fn, d epsilon fn of psi, and d delta epsilon of alpha. It can be defined easily because now alpha can be represented at least as phi of psi, and then shift of alpha can be represented as phi of psi plus s. It is well defined because this is important remark. Because psi now has a distribution which is equivalent to Lebesgue mesh. So when we shift it in any epsilon, then the distribution remains to be equivalent to the Lebesgue measure and is equivalent to initial distribution. So the result of the shift does not depend on the representation of phi. And this is totally not true in the infinite dimensional case for arbitrary shift. We will see this in the future. But in one-dimensional case, the shift of random variable is defined easily and correctly. And then one can define this one. Let it be T epsilon of alpha. And then this is T epsilon of alpha minus alpha divided by epsilon. So then we know that this converges to f prime of psi. One can find fn in such a way that it is close in two sets to this one. It's easy. And then we will get a convergence of this when epsilon tends to 0. And of course, the limit must coincide with this f prime. Due to the property of stochastic derivative that it is closed, closed linear operator. From this point of view, finally, we understand that the following relation holds. If we have the random variables of W1, now such that this is a technical moment. It will be used in the proof, such that d alpha belongs to n infinity. Then d alpha is the limit the epsilon tends to 0, and here is t epsilon alpha minus alpha divided by epsilon. So in some cases, we still have a more or less familiar definition of derivative which we use in analysis. That's all for our lecture today. Maybe somebody have questions or comments, please. Okay, if there are more questions, then thank you and see you next week. Bye.